In this video we're going through a bit of a refresher of kinematics. Most of it's stuff that we've seen previously and moves us into solving inverse kinematics problems. So firstly, forward kinematics. Remember, we have a robot arm that consists of a whole lot of rigid bodies or links which are connecting together a whole lot of joints. In this case, a whole lot of revolute joints, but they may be prismatic as well. Now, if we know all the angles and displacements of these joints, so angles for revolute joints and displacements for prismatic joints, we can compute our end effector position. And we can add them all up and create a DH sort of linkage between them all and work out what the position of the end effector will be given all those joints. And we only have one possible solution to this because we know what all our angles are, and therefore our end effector position as well is known. Now, inverse kinematics goes in the opposite direction. So if we know the end effector position, or the desired end effector position, where we actually want to go, here we need to work out what all the joint angles or displacements are when we've got prismatics to get to this actual position. So inverse kinematics allows us to compute our joint angles based on a desired end effector pose, where we actually want to be. Now, previously in forward kinematics there was only one solution. In inverse kinematics, there might be one solution, but in many cases there'll be more than one. There may be many solutions that, based on the position and layout of our different joints, we can reach that position based on a whole lot of different joint numbers. It really depends on the number of degrees of freedom and how we align those different degrees of freedom within our robot. When we think about our own arms and things like that in the different joints, there's quite a few different ways we could reach a particular point. So we could reach the same end effector pose and take several different paths to get to that pose. Now, there's quite a few different techniques that we can use for inverse kinematics. Here's a few different ones. Fundamental geometry and trigonometric reasoning. That's what we'll do in the next few examples. There's algebraic solutions, iterative ones, Jacobian inversion and Jacobian transformation, cyclic coordinate descent, and evolutionary approaches like genetic programming, evolutionary algorithms, genetic algorithms and things like that. Generally, it's recognized that there isn't one perfect silver bullet approach that does everything. And because there's several different solutions potentially, or maybe quite a few different solutions, it can be a bit more rigorous to try and actually come up with them. Let's look at the basic principles of using our geometric approach. Now, firstly, we draw diagrams and label everything on the diagrams. And particularly, we'll be trying to draw things in terms of triangles and things that we can compute. We'll also be using the arctan2 function, and we'll be discussing that in the next video about why it's important and what it actually does. Now, remember various things like Pythagoras' theorem. This will be very helpful when we're solving some of the diagrams, and also the cosine rule, where we can compute angles or side lengths for non-right angled triangles. This is all back from high school maths as well. Very useful to use in these sort of circumstances. A few reminders about drawing diagrams. Remember, we're drawing our manipulator diagram consisting of joints and linkages, and we draw these as revolute joints that look a bit like a cylinder, or prismatic joints that look like a box. This helps us visualize what's going on and works out whether we're actually fitting the diagram. We then want to label them all, so we label them joint 1, joint 2, joint 3, and so on, and we label them theta 1, theta 2, theta 3, and link 1, link 2, link 3 sequentially. We've got our revolute joints, our prismatic joints, and our z-axis will pass through the center of rotation of the revolute joint, or the center of movement, the translation for our prismatic joint. And so we have those same rules that we had before about assigning our joints for each of the next axes, and we use our right-hand rule to assign the extra variables in our coordinate frame, like the y variable, for example.